on to section 4.5, the real zeros of a polynomial function. Okay, this section's a little bit more theoretical than some of the ones in the past. The real goal is to find zeros of polynomials and maybe to factor. And the idea of factoring a polynomial and finding its zeros are intimately related problems, as we'll elaborate on. So the techniques we'll use to find these zeros will make use of the remainder and factor theorems. Descartes' rule of signs will tell us about possible numbers of certain types of zeros of a polynomial. The rational zeros theorem will give us potential rational roots, rational zeros of a polynomial function. And this will be quite helpful in factoring. We'll solve polynomial equations, and we'll use the theorem for bounds on zeros to find, to narrow down the location, I should say, of where zeros might be. I might not be able to find them specifically, but I can tell you they lie in a certain interval, for example, under certain conditions. And we'll use the intermediate value theorem, actually a result from calculus, to indicate when we might find some zeros of a polynomial function. We'll start with the division algorithm for polynomials. Likely you're familiar with the division algorithm for integers. If you divide one integer by another non-zero integer, then you get a quotient and you get a small remainder, the remainder being smaller than the divisor. Same idea here, except we're doing it for polynomials. And the idea of size, in a sense, is related to the degree of the polynomial. So if f and g denote polynomial functions, if g is not the zero polynomial, because we're going to divide by z, then there are unique polynomial functions q for quotient and r for remainder, such that f of x divided by g of x equals q of x plus r of x over g of x. Think of this in terms of numbers, and that's the exact type of relationship you get when you do long division. We'll deal with this division algorithm and some of its uses using long division of polynomials. If we were to multiply through by g of x or cross multiply, then we get f of x is q of x times g of x plus r of x. Same kind of thing we had with numbers. Q is the quotient, r is the remainder, and we get these relationships. These we will use in the setting of polynomials and finding roots and some conditions that'll guarantee that we have a root of a polynomial. The condition on r of x is it's either the zero polynomial, in which case there was no remainder, or a polynomial of degree less than that of the divisor function g. So remainder in degree is less than the degree of the divisor function, the g of x function. So when you do the long division, you simply keep going, as it were, until you get a remainder that's smaller in degree than the divisor function. F of x is the dividend, g of x is the divisor, q of x is the quotient, and r of x is the remainder functions, as I mentioned. We're not quite in a position to prove that, but we can use it to prove some other useful stuff. Two useful things are the remainder theorem, which says, let f be a function, polynomial function. If f of x is divided by x minus c, then the remainder is f of c. In particular, if f of c is 0, then we have a remainder of 0, and we have a divisor of polynomial function f, and we have a root of that function, as we'll see. The factor theorem says, if f is a polynomial function, then x minus c is a factor of f of x, if and only if f of c equals 0. So before we look at the proofs, a quick comment about the factor theorem. This tells us finding zeros of polynomial functions and finding factors of this form, they're called linear factors. This is the exact same problem. So Finding zeros and finding linear factors, same problem. Factor theorem tells you that. So let's look at proofs of these. Given the division algorithm for polynomials, the proofs aren't very hard. Remainder theorem says, let f be a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. With an idea towards finding zeros of polynomials, we want that remainder to be 0. And that's how we'll use this remainder theorem. So let g of x be x minus c. We're going to take f of x and divide it by g of x, just to put it in the same notation we had for the division algorithm. Division algorithm tells you that f of x divided by g of x will be some quotient polynomial plus r of x divided by g of x. And the deal with r of x is it's either the 0 polynomial or a polynomial of degree less than that of g of x. But g of x is a first degree polynomial, so r of x must either be the 0 polynomial or a polynomial of degree 0. It must be a constant, no matter how you slice it. For some technical reasons to be elaborated on in the next section, when we talk about the fundamental theorem of algebra, the constant function of 0 usually doesn't count as a polynomial. Polynomials can be constant functions, but not the 0 function, is a common way to deal with the term polynomial. It's common terminology. So anyhow, r of x must be a constant. Let's call it capital R. So we know the remainder will be constant from the division algorithm. Denote that constant as r. Now let's establish the claim. Division algorithm then reduces to f of x divided by x minus c equals the quotient q of x plus r divided by x minus c. Simply this rewritten with g of x replaced with x minus c and the r of x, knowing it's some constant, replaced with r. Good to go, even if that constant is 0 in this statement. So multiplying both sides by x minus c, we get f of x equals x minus c times q of x plus the r. The denominators canceling from these two terms when we multiply both sides by x minus c. So in the event that x equals c, we have from this formula here, which by the way is valid for all x, previous formula. Of course, we couldn't have x equals c because we had x minus c's in the denominator, but this formula is valid for all x, including x equals c. Then set x equal to c, we'll have f of c equals c minus x times q of c. Wherever there's an x, I'll replace it with a c. This gives us a c minus c. Well, that's 0 times something. 0 times anything is 0, plus the remainder r. No c's in that, no x's in that. And we see that f of c equals that remainder r, and that's what was claimed. The remainder is f of c. So f of c equals r, r was the remainder. So we've established the claim in terms of relating the remainder to the value of the function at this point, x equals c. It's not so much the remainder theorem as it is the factor theorem that we're interested in. We'll use the remainder theorem to prove the factor theorem. This one says polynomial function f, x minus c is a factor of f if and only if f of c equals 0. So here comes the usefulness of the remainder theorem. Suppose f of c equals 0. Well, the remainder theorem just told us that f of x, when divided by x minus c, will factor into x minus c times q of x plus f of c, and that's what we had in the remainder theorem. And we know this f of c will be under this supposition 0. We're assuming f of c equals 0. Plug that in there. That disappears. We get x minus c times q of x equals f of x. Well, that means x minus c is a factor of f of x, because f of x equals x minus c times something. That something is whatever q of x is. But to say we have a factor of a polynomial function is the same thing as to say we have a factor of a whole number. You factor 10 into 2 times 5. 2 is a factor of 10, and 5 is a factor of 10. Here we factored f of x into x minus c times q of x. Then x minus c is a factor of f of x. So is q of x. The claim was x minus c was a factor of f of x in this case. So if f of c equals 0, then x minus c is a factor of the polynomial function. Conversely, suppose x minus c is a factor of f. That means f of x equals x minus c times something. Let's denote the something q of x, very suggestive of the remainder theorem or the division algorithm. But x minus c times something, doesn't matter what we denote the something as. Then if we plug c, x equals c in, we get f of c equals c minus c times q of c. Well, c minus c is 0. We get that 0 out yet again. And so in this case, f of c equals 0. So f of c equals 0 if and only if x minus c is a factor of f of x. Are you good at factoring? Second degree polynomials, pretty good at it. Third degree polynomials, a little spotty at it. You got a few tricks. And factoring's hard. Well, if factoring's hard, that means finding zeros of a polynomial is hard as well, because they're the same puzzle, exactly the same problem. Next, let's do an example. Number 18 says, consider f of x equals x to the 6 minus 16x to the 4th plus x squared minus 16. And consider x minus c, that is x minus. So we're going to use the remainder theorem to find the remainder when f of x is divided by x plus 4, this x minus c. Right? I write it explicitly in terms of the x minus c stuff. Better to see what we're doing and see what the value of c is given above. Having done that, use the factor theorem to determine whether x minus c, x plus 4, is a factor of f of x. Okay, first use the remainder theorem to find the remainder when f of x is divided by x plus 4. Remainder theorem says that that remainder will be f of c, where c is negative 4. That's why I've written it in terms of this up here, so you can more explicitly see the negative 4. So if we take f of x divided by x plus 4, remainder will be f of negative 4. Plug the negative 4 into the function, do the arithmetic, double check it if you like, or trust me, the remainder, the value is 0. And so by the factor theorem, the remainder, the remainder is 0. Getting ahead of myself on factor theorem. Remainder theorem tells you f of c, f of negative 4 is the remainder. The remainder is 0. All right, now the factor theorem says, well, if the remainder is 0, then we found a factor of the original polynomial function. So by the factor theorem, since f of c equals 0, then x minus c is a factor of the polynomial function. That is x plus 4, x minus negative 4. X plus 4 is a factor of f. And that's all they ask us to do at this stage. Can you factor this? Well, I could do long division and divide it by x plus 4. I know it'll go in, I want to say a whole number of times. I know there'll be no remainder, is a better way of saying it, if we divide this polynomial function by x plus 4. What we'll get from that will be some 5th degree polynomial, and I don't know if I can factor that or not. But I can start factoring this because we found a factor of it, and we could factor it using a long division. Back to the notes. The next theorem is not the fundamental theorem of algebra, but it's related to the fundamental theorem of algebra. And it tells us how many real zeros a polynomial function can have. A polynomial function cannot have more real zeros than its degree. We've got the equipment to prove that, so we will. We'll use the factor theorem to show this. It turns out the degree of a polynomial tells you how many roots it has. How many roots it has if you'll let me use complex numbers. And that's where the fundamental theorem of algebra comes in. So the fundamental theorem of algebra, we have to have a discussion in the setting of complex numbers to really state the fundamental theorem of algebra. But this is a step in that direction. We will address this in the next section. Theorem 4.5.d. All right. So claim is related to how many real zeros a polynomial can have. It's no more than its degree, is the claim. Well, by the factor theorem, if r is a real zero of polynomial function f, then f of r equals 0. That's the meaning of finding a zero of the function. And so x minus r is a factor of f. So every time we find a real zero, we have a factor of the polynomial function. Now, each real zero corresponds to one of these factors, and these factors are degree 1, x to the first power minus 1. They're little first degree polynomials. So if for every zero you find one of these linear factors and you multiply all of those together, that gives a polynomial that is a factor of f. A product of factors is a factor. And the degree is equal to the number of first degree factors. For every root, you found one of these factors. Multiply those factors together. You have 1 for each real zero of the polynomial, and you'll get a polynomial then of degree equal to the of degree at most the number of real zeros. Could be x minus r is a factor of multiplicity 2. We haven't addressed multiplicity. That's part of the problem. We also haven't addressed all the zeros. We're only talking about real zeros here. But the degree of a polynomial factor of f can exceed the degree of f. I can't go through and do division of a 5th degree polynomial by a 7th degree polynomial. I can't divide by a larger degree polynomial. It won't go in a sense. So we'll have nothing but remainder in that case. But in this case, we have a product of a bunch of factors. How many factors? It's the number of real zeros, factors. Multiply them together, they produce a factor, which is a polynomial of degree, number of real zeros of this polynomial function. That's a factor of the polynomial itself, then the degree of that factor cannot exceed the degree of f. That is, the number of real zeros cannot exceed the degree of the polynomial function. It's stated in terms of not degrees here, but number not exceeding. So same idea. So this says, yeah, I got a 5th degree polynomial. It's got at most 5 real zeros, 5 real roots. Doesn't tell me anything about where they are, how to find them, but it puts a cap on how many there are. Oops, let's return to the notes. And a statement about the fundamental theorem of algebra. As we'll see in the fundamental theorem of algebra, in the next section, the total number of real and complex zeros, counting multiple zeros according to their multiplicity, it's a little trick on the counting, how the counting is done, equals the degree of the polynomial. So degree of the polynomial equals the number of roots for the number of zeros. You got to let me use complex numbers for that to hold, and you got to let me count zeros according to their multiplicity to get that to hold. We could generalize the factor theorem and say, if you'll let me use real and complex zeros, then I can factor an n-degree polynomial into a product of n linear terms, each linear term corresponding to a zero. Multiple linear terms, high multiplicity zeros of that polynomial function. But the books totally balance as soon as you go into the complex setting. Here, if we're going to restrict ourselves to real numbers, which I'm fine with up to this point, I'm going to have to throw around the word at least a lot. There's at least this many whatevers. Yeah, where's the rest of them? Well, they're out there in the complex realm. So we don't find maybe all of the zeros of a polynomial if we're only going to stick to the real numbers. So that's why you see this at least stuff several places. Descartes' rule of signs gives you an idea about how many positive roots and how many negative roots a polynomial function can have. So let f denote a polynomial function written in standard form. You'll recall that was decreasing powers of x, highest power of x first, second highest power of x, blah, 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 with a constant term on the far right. The claims are the number of positive zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer. Okay, we'll illustrate it with an example, but what they're trying to get at here is write the coefficients out in order. You may skip those that are zero or ignore them, and you're looking for the number of variations in the sign. That is, when a coefficient, reading from largest power of x to lowest power of x, that's the standard form part, you're looking for places where the coefficients change from positive to negative or change from negative to positive, overlooking the zeros in this case. If there's, say, 5 such variations of signs, if it goes positive to negative, back to positive, back to negative, back to positive, back to negative, maybe it changes and it stays negative for a few times, but if it changes 5 times, that tells you the number of positive zeros of that polynomial function is 5 or 5 less an even integer. So subtract 2, 5 or 3 or 1. It doesn't make sense to subtract 2 from that because we're counting something, number of positive zeros. So that's what the less an even integer part means as well. For negative zeros of the polynomial function, claim is this either equals the number of variations in the sign of the non-zero coefficients of f of negative x, or else equals that number less an even integer. So when looking for negative zeros, you consider f of negative x and then do the same thing that we did up here. Look for changes in sign when read from highest power of x coefficient to lowest power of x coefficient, ignoring the zero coefficients. Count those. That's either the number of negative zeros or the number of negative zeros is that minus 2 or 4 or 6 or whatever, as long as you keep that quantity non-negative. Let's illustrate that with an example. So the wording of it is arguably a little bit clumsy, but here's a polynomial. Give the maximum number of real zeros that each polynomial function may have. Then use Descartes' rule of signs to determine how many positive and how many negative zeros each polynomial function may have. Don't try to find those zeros because we don't have the equipment to do that. Well, we've got a 5th degree polynomial, x to the 5th. Notice it's written in standard form. All the coefficients are either positive 1 or negative 1. It's 5th degree. So by the number of zeros theorem, it can have a maximum of 5 real zeros. And that's all I know. in terms of number of zeros, number of real zeros. Descartes' rule of signs, let's look for positive zeros or negative zeros. So the coefficients, omitting any coefficients which are zero, and there are none in this particular case, we have the coefficients are 1, negative 1, positive 1, negative 1, positive 1, negative 1. There's 5 sign changes. 1, 2, 3, 4, 5. 5 sign changes. So Descartes' rule of signs tells you that the number of positive zeros is 5, or 3 or 1. I got to do that reduced by 2. So I guess in a best case scenario, we would have 5 real zeros and all 5 of them would be positive, but I don't know. There's ambiguity in this still. How about the Descartes' rule of signs for the number of negative zeros? For that, consider f of negative x, as we said. So we'd have negative x to the 5th power minus negative x to the 4th power, and so forth. Well, these even exponents absorb those negative signs. The odd exponents, I would say, spit out those negative signs. So this will simplify to negative x to the 5th minus x to the 4th minus x cubed minus x squared minus x minus 1, multiplying out. And the coefficients then go, eliminating the 0 coefficients, but there are none. Negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. There's 0 sign changes here. Well, this is a definitive answer. The number of negative zeros is 0, so no ambiguity there. So it has a maximum of 5 real zeros, and we know that 5 or 3 or 1 of those real zeros is a positive number. At least we know this. There's at least one positive real root. Can I guess it? I would guess it's 1. We'd have 1 minus 1 plus 1 minus 1 plus 1 minus 1. Yeah, just lucky observation. 1, x equals 1 is a root of this polynomial. I know it has at least one, it possibly others. But with the information we have, can't give you a precise answer on what the zeros are, especially not for 5th degree polynomial. But I can tell you a bit of information. It's got at most 5 real zeros, and at least one of those zeros is positive. Possibly it has 3 positive real zeros. Possibly it has 5 positive real zeros. I don't know. I was lucky to notice it has to have at least one. And by the way, x equals 1 is that 0, is a 0. Possibly there's more positive real zeros. I don't know. And I don't know. This is complicated stuff to get precise answers tied down. All right, so actually finding the zeros of a polynomial function is an extremely difficult problem. In fact, it's an impossible problem in some sense. I refer you to a senior level class on algebra that elaborates on exactly what this means. If you had a 2nd degree polynomial and you'd use complex numbers, you're good to go. You got the quadratic formula that will give you the zeros of a 2nd degree polynomial, but you might need some complex numbers there. 3rd degree polynomials, well, it turns out there's a formula for those as well that may require complex numbers. 4th degree polynomial, it turns out there's a formula there that may require the use of complex numbers. 5th degree polynomial and higher degree polynomials, there's not a formula. There is not an algebraic formula. So that gives you a little bit of insight on what this impossible means. Just like there's a quadratic formula for 2nd degree polynomials, there's also a formula for 3rd and 4th degree polynomials. But it can be proved that there is not such a formula for 5th degree polynomials and higher degree. So that's what this impossible comment means. It's algebraically impossible. Doesn't mean there aren't other ways, but there aren't other algebraic ways. And that's a deep topic and an idea that's only a couple hundred years old, turns out. So we'll do what we can do. These ideas about impossibility sort of, in hindsight, tell you why we've done the problems we've done. Why don't I just make up some polynomial and say, here, factor this? Well, the possibilities can't be factored algebraically. So you have to stick to the textbook examples. The big point is, this is hard stuff. Factoring polynomials and finding roots of polynomials, that's hard stuff. In fact, this is an area of research that goes on to today to describe where the zeros of a polynomial might be. And we'll have a result along those lines related to the real number line. But finding zeros, actually finding the zeros, that's quite an intense problem. So we're going to do what we can do. The next theorem allows us to make a list of possible rational zeros. So we'll get a nice little finite list of possible rational zeros of a polynomial with integer coefficients. And from there, we could maybe find some factors. We could use the factor theorem to see if that produces factors. The rational zeros theorem, which we do not have the ability to prove with our current level of knowledge, says for f a polynomial function of degree 1 or higher of the form f of x equals a sub n x to the n, a sub n minus 1, x to the n minus 1, down to the constant term, with the conditions that a sub n is not 0. So it's actually a degree n polynomial function. A sub 0 is not 0, so the constant term is non-zero. If the constant term was 0, if this wasn't there, we could factor x out and modify this so that the constant term is 0. So there's no loss in either of these hypotheses without loss of generality. We're dealing with a general polynomial function, and it's written in standard form, right? Decreasing powers of x. And we're requiring that each of these coefficients be an integer. This works from theory based on polynomials with integer coefficients. The claim is, if P over Q in lowest terms is a rational zero of f, then P must be a factor of a sub 0, and Q must be a factor of a sub n. So here's what we're going to do to use this. We'll find all factors of a sub 0. We'll find all factors of a sub n. We'll take quotients of them, and that'll give a list of possible rational zeros of a polynomial. We could then plug them in and see if they work, see if they actually are zeros of the polynomial. And that could lead us to linear factors by the factor theorem. For example, consider this polynomial function, 3x to the 5th minus x squared plus 2x plus 18. List the potential rational zeros. Don't attempt to find the zeros. So this one, we're just making a list of zeros, potential rational zeros. All right, well, we need factors of 3 and factors of 18. Factors of 3 are easy, as a plus or minus 1 and plus or minus 3, integer factors of 3. The factors of 18 is a little lengthier list. Divisors of 18 are 1, 2, 3, not 4, not 5, 6, 9, and 18, plus or minus. So we actually get 1, 2, 3, 4, 5, 6. We get a dozen of those. So here's a list of all factors of the constant term. Here's the factors of the leading coefficient. The rational zeros theorem said if we have a rational zero of the polynomial function f, then the numerator p is a factor of the constant term a sub 0, and the denominator q is a factor of the leading coefficient. So here's what we need to do. We need to take all of the factors of a sub 0 and divide them by all of the factors of a sub 5. Factors of 18, divide them by factors of 3. Okay. Plus or minus 1, you take all 12 of these things, you divide them by 1 or negative 1, you get the 12 things right back. So the division by 1 or negative 1 really contributes nothing new here. Divide by plus or minus 3, and we pick up some non-integer rational numbers. we'd have plus or minus 1 divided by plus or minus 3. That'll yield plus or minus 1/3. Plus or minus 2 divided by plus or minus 3. That'll yield plus or minus 2/3. Plus or minus 3 divided by plus or minus 3 will yield plus or minus 1, and it's already in the list. 6 and 3 would produce 2, plus or minus, it's already in the list. 9 divided by 3 is 3, plus or minus, it's already in the list. 18 divided by 3 would produce plus or minus 6, and it's already in the list. So there's some redundance in this. But we've got a total of, what was it, 6, 7, 8, I think it's 16 possible rational zeros. Could they all be zeros? No, this has at most 5 real zeros because it's a degree 5 polynomial. We know the maximum number of zeros. So certainly some of these are not zeros of that function, and possibly some of them are. How would you find if they are? Plug them in and see if the output is 0. Returning to the notes, we'll take this process through in more detail in an upcoming example. The textbook lists the following steps for finding the real zeros of a polynomial function. Step 1, use the degree to determine the maximum number of real zeros. Secondly, use Descartes' rule of signs to determine the possible number of positive zeros and the possible number of negative zeros. This will be that thing where you have to reduce it by 2. So that will come with some ambiguity. And neither step 1 nor step 2 tells you what the zeros are. You're getting information about how many there are and how many there may be which are positive and how many there may be which are negative. Step 3. If the polynomial has integer coefficients, which is likely to be the case in practice, use the rational zeros theorem to identify those rational numbers that potentially could be zeros. Okay, now we're getting somewhere. Now we're talking about potential zeros. Step 3b says use substitution, synthetic division. I will not use synthetic division in these notes. It's explained in the book. Or long division. We will use long division. It's more rational, more reasonable, probably is the word I should use. But use substitution or division to test each potential rational zero. Each time that a zero is found, and thus a factor is found, repeat step 3 on the depressed equation. Wow, bummer. That is, you found a factor, in some sense, factor the polynomial function and consider a polynomial function now of a lower degree, the factored, one of the factors in the factoring. That's what they mean by depressed equation when they say that. In attempting to find the zeros, remember to use, if possible, the factoring techniques that you already know. Special products, factoring by grouping, and so on. Really, factoring by grouping is possibly the most useful of these. Use the tricks when you can see that they apply, because this could take a while. Let's do number 54. It says use the rational zeros theorem to find all the real zeros of this thing. It's a 4th degree polynomial function. Use the zeros to factor f over the real numbers. Okay. It must be that this function it's likely that this function has only rational zeros. They've asked us to find all the real zeros. And except for 2nd degree polynomials, we're not good at that. Unless they happen to be rational, because now we got that little trick about finding rational zeros. Okay. Let's use the rational zeros theorem by finding the divisors of the leading coefficient, 1, plus or minus 1, factors of a sub 4 equals 1 or plus or minus 1, and find the divisors, the factors of the constant term. A sub 0 equals 8. That will give us factors of plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Those all divide 8 over the integers. So the rational zeros theorem tells us if we have a rational zero in reduced form, then the numerator is a factor of a sub 0, the constant term, and the denominator is a factor of 1. So all we have to do then is take the factors of the constant term, factors of a sub 0, plus or minus 1, 2, 4, and 8, and divide them by plus or minus 1. So that simply reproduces plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So we didn't get any fractions this time. What made that work really was the leading coefficient is 1. So in that case, we'll actually be getting integers out in the rational zeros theorem. So let's use the factor theorem by simply plugging in and seeing if we get 0 out. If we do, factor theorem will tell us that we found factors. So plug in positive 1, negative 1, positive 2, negative 2, positive 4, negative 4, positive 8, negative 8. So I'm going to plug in 8 different things. Here's what we get in those 8 cases. Trust me. So time consuming and tedious. I'm looking for zeros. There's an output of 0, there's an output of 0, and there's an output of 0. So we found 3 zeros of this function. Negative 1 is a 0, a root. 2 is a root, and negative 2 is a root of this polynomial function. Remember, we're using the term root and 0 interchangeably. So we found 3 of the zeros. How many zeros could there be? Fourth degree polynomial, there could be 4 real zeros. Well, we found 3 of them. By finding zeros, the factor theorem tells us we've also found factors. Since negative 1 is a 0 of the polynomial function, then x minus negative 1, that is x plus 1, is a factor of the polynomial function. 2 is a 0, x minus 2 is a factor. Negative 2 is a 0, x minus negative 2, that is x plus 2, is a factor. So we found 3 factors, x plus 1, x minus 2, and x plus 2. So these 3 things are factors of f of x, the polynomial function. So the product of them is also a factor. If you like, we can multiply these things out. Let me multiply them out. I got my reasons, and these reasons are elaborated on the next slide. So we found 3 factors. There should be a 4th one associated with a 4th root. So let's take these 3 factors, multiply them together. Notice we've got a special product here. This produces an x squared minus 4. Foil what we've got here, and it will produce this thing here. I multiplied out. I wouldn't do that unless it was a good idea. So how are you going to find this last real root if there is a 4th real root? Let's do long division. F is degree 4 polynomial, then there must be another first degree factor. Also, this first degree factor will yield another 0 of f. It should have 4 zeros. It's unlikely to involve an irrational number. We might suspect that one of the zeros is a 0 of multiplicity 2. It's unlikely to involve complex numbers. In fact, it's impossible for it to involve complex numbers in this case. Let's not get into that, but let's do long division. So let's take the f of x function and divide it by the product of those 3 factors. This is what we had at the bottom of the previous slide. Do the long division. Let me not go into the details on that. Of course, feel free to pause the video and double check all this work. But we'll get a quotient of x minus 2 and a remainder of 0. Ooh, a remainder of 0. That tells you this thing here is actually a factor of the original polynomial. X minus 2 divides f because we got a remainder of 0. In fact, what we have here is x minus 2 times this thing here equals a polynomial. This thing here was, before we multiplied it out, was x plus 1 times x minus 2 to the first power times x plus 2. what we've demonstrated here is, since the remainder is 0, then this is also a factor. So x minus 2 is a factor due to this factor, which x minus 2 divides, and due to this long division. Actually, x minus 2 is a factor of multiplicity 2. So this is kind of a big deal. We factored this 4th degree polynomial, a little bit hit or miss because we used the rational roots theorem, but it worked out awesome. All the roots were rational. In fact, all the roots were integers in this case. So here we have f of x factored as they desired. Notice it factored into 4 linear terms, 1, 2, 3. This one I count twice to get the books to balance, and a 4th one. It was a 4th degree polynomial, and it has 4 linear factors. Awesome. Had it had complex zeros, this wouldn't have worked out quite as cleanly. There's a possibility we could have still found all the zeros, maybe using the quadratic equation. If it had had some irrational zeros, we may have been able to find all of the zeros as well. Really, we're going to put a lot of weight on the quadratic formula if we deal with irrational roots and complex roots. Returning to the notes, a quadratic of the form ax squared plus bx plus c is called irreducible if it cannot be factored over the real numbers. That is, it's prime over the real numbers, a term we used at some point in the past, might have been in the review sections. So this can't be factored. We can tell this can't be factored by looking for roots. I would be hopeful that this 2nd degree polynomial equation, 2nd degree, could be factored as a product of 2 linear terms. And you know what? It can be, if you'll let me use complex numbers. But this talks about only real numbers. Complex numbers, if I can use those, I can do a lot more stuff. If you don't let me use those, which is the rules we're playing by in this section, then this idea of irreducibility comes up. There is no such thing as irreducibility of a quadratic if you'd let me use complex numbers. And I can tell you how to factor it. It turns out I'll use the quadratic formula. I'll find the roots, that'll tell me factors, and I can factor it. But staying away from complex numbers and restricting our attention to real numbers, then these irreducible factors are on the table. For example, consider x squared plus a, where a is greater than 0. This doesn't have any zeros. X squared plus a would be positive because x squared is non-negative, and we said a is positive. You add a non-negative to a positive, you get a positive. So this is always greater than 0. In particular, it never equals 0. If it never equals 0, then it has no zeros, and so by the factor theorem, it has no linear factors. It can't be factored. It is irreducible. So here's an example of an irreducible quadratic, no x term, that's okay. The b parameter given here must be 0. So x squared plus a, where a is positive, yields some examples of irreducible quadratics. Okay. Here's how irreducible quadratics and linear terms fit together if you restrict yourself to real numbers. It says every polynomial function with real coefficients can be uniquely factored into a product of linear factors, things of the form ax plus b, and or irreducible quadratic factors, things of the form stated up here, sum ax squared plus bx plus c. Proving that is beyond our abilities. It's a useful observation. You'll use it actually in Calculus 2, as we'll talk about in a second. And you know, it doesn't tell you anything about how to do this. It only tells you it can be done. So we're stuck with that again. I knew an n-degree polynomial has at most n real zeros, but I don't know what they are. I know how to look under certain circumstances for rational zeros, but that becomes the long story of dealing with this. These results are telling you sometimes how to find the zeros, but oftentimes it's just telling you certain things exist, but it's not telling you how to find them. And so we're stuck with that, even in some upper level settings. This fact that you can take a polynomial and write it as a product of linear factors and irreducible quadratics. This is pre-calculus. You will see this in calculus 2 when you do something called integration of rational functions by partial fractions. You'll use the factoring of the denominator of a rational function. You know what a rational function is, the quotient of polynomials. You'll take that denominator and you'll factor it. You'll factor it into linear factors and irreducible quadratics. And that will be doable because you'll be doing textbook examples. I mean, even doing this for small degree polynomials potentially could be quite monstrous, but you'll be working textbook examples there and you'll see this idea again. Remember this for calculus 2. Every polynomial function can be written as a product of linear factors and irreducible quadratics. Your goal at that stage will be integration of rational functions, but the techniques will require a heavy dose of algebra to get these started, and then you'll work on the calculus part. Oops. As a corollary to this idea, we've got the following, the proof of which depends on the n behaviors of odd degree functions. And states a polynomial function with real coefficients of odd degree has at least one real zero. See, that can be addressed in the setting of something called the intermediate value theorem, which we'll state. Let's just save this for later. The idea is if it's odd degree, it must be big and positive on one side and big and negative on the other side. Well, if it's positive on one side and negative on the other and continuous, and polynomial functions are continuous, then it's got to be zero somewhere out there. So this guarantees at least, it's another one of those underestimations potentially, at least one real zero. Odd degree polynomial functions, at least one real zero. But that's best discussed in the setting of the intermediate value theorem. I bring it up here because the book put it in this order. Another little definition and something that will allow us to go through under certain circumstances and have a certain place where zeros could be. So this puts an upper and a lower bound on where the zeros might be for a polynomial function under certain conditions. First, the definition says a number capital M is an upper bound to the zeros of a polynomial f if no zero of f is greater than capital M, upper bound. The number lowercase m is a lower bound if no zero of f is less than lowercase m. Accordingly, if lowercase m is a lower bound and capital M is an upper bound, all the zeros lie between those. So we got a lower bound, we got an upper bound, and all the zeros must be in between there. How do you find these capital M's and lowercase m's then becomes the question. And that's a question we can answer under certain circumstances. So even finding these bounds, we're going to be limited in the technique. For polynomials with integer coefficients, knowing the values of lower bound little m and upper bound capital M may enable you to eliminate some potential rational zeros. For example, if I've got these bounds and I know, say, none of these zeros are greater than 5, and I apply the rational roots theorem and I get, maybe plus or minus 10 and plus or minus 30 as potential rational zeros. Well, they couldn't be if they're bigger than the upper bound on the zeros. And similarly with lower bounds. So we get an interval of this form if we can find this uppercase m and lowercase m, and we know all the zeros lie in there. The following theorem, bounds on zeros, gives some conditions under which we can find capital M and lowercase m. And they're pretty specialized conditions and rather awkward to state verbally, but we'll go through the proof of this. Part 1 is not too strange. Part 2 is a little more complicated. We're simply claiming something is positive or something is negative in all of the following stuff in this theorem. And it just boils down to positive times positive, negative times positive, you know, the behaviors of products of real numbers. And then the fact that if I add a bunch of positive stuff together, I get something positive. If I add a bunch of negative stuff together, I get something negative. Statement is, let f denote a polynomial function whose leading coefficient is positive. If capital M greater than 0 is a real number and f of x equals x minus capital M times q of x plus r of x plus r, constant. Such r exists by the division algorithm for polynomials. We're dividing f by this first degree polynomial. So we get a 0 degree polynomial. We get a constant as the remainder, where the coefficients of q are non-negative and remainder r is non-negative, then m is an upper bound to the zeros of f. So if such a positive m exists, such that when you do this division, we have the following situation: coefficients of q are non-negative and the remainder is non-negative, then m is an upper bound to the zeros of f. So like I said, this works under certain circumstances, and that's the conditions. You do this division and you get the coefficients of q as needed and you get the remainder as needed. Upper bounds. Lower bound. Okay, it'll be a similar process. This one's just a little more clunky to describe. If lowercase m less than 0, one's positive, one's negative, is a real number and f of x equals x minus lowercase m times q of x plus remainder capital R, where the coefficients of q in standard form, listed in decreasing order of powers of x, followed by r, alternate positive or 0 and negative or 0, then lowercase m is a lower bound to the zeros of polynomial function f. Okay, let's look at a proof of that. If you're opposed to proofs, this might be a good one to skip because this is going to be moderately involved. First part, not so much. Second part, just awkward. It's based on elementary ideas, but still. Let's look at part 1, the first claim. Suppose there is a capital M greater than 0, a positive real number, such that we get the factoring, as mentioned, with the coefficients q being non-negative and the remainder r being non-negative. We're going to show m is an upper bound on the zeros of f. That is, we're going to show there isn't anything bigger than m that's a 0 of the polynomial function. We will do so by taking x greater than m and showing that f of x is not 0. So anything bigger than m can't be a 0 of the function. So the zeros of the function are less than or equal to m. That is, m is an upper bound on the zeros. So how to do this? Take x greater than m, then x minus m is greater than 0. Subtract m from both sides, property of inequalities. And since we do know x is greater than m and m is greater than 0, and started with that as hypotheses, then q of x is greater than 0 because all the coefficients of q are non-negative. We've plugged in something that's positive. So unless q of x is a zero function, in which case we were dealing with a constant function to start with, so that's a deviant case, we get q of x is greater than zero. All the coefficients are, let me say positive. That's imprecise, but let me say it anyhow. All the coefficients are positive, and we plugged in a positive x value. Well, that's going to give a positive output. Okay, not all the coefficients are positive. They're all non-negative. I do need at least one of them to be positive to get the strict inequality. But you plugged a positive number into a polynomial with positive coefficients, you'll have a positive output. Not a problem. So we get q of x is greater than 0. Now we know x minus m is greater than 0. This is positive. We just showed q of x is greater than 0. This is positive. And we hypothesize that r is non-negative. So we've got positive plus positive or 0. Well, that's going to yield something that's positive. So for such an x value, f of x is strictly greater than 0. F of x is positive. So f can't have any zeros, x, which are greater than m. So if we have a 0 of this function f, it's going to have to be less than or equal to m. That is, m is an upper bound of the zeros on f as claimed, and told you so. The argument ultimately turned out to be not too complicated. It was simply positive times positive plus non-negative yields a positive. The second part holds similarly, but we have to break into 4 cases. So let's take a shot at that. Now, suppose m is less than 0, real number. We have f of x factored into x minus m times q of x plus r, where the coefficients of q in standard form, followed by r, alternate positive or 0 and negative or 0. Okay. Suppose q of x looks like this. What that means is, if I look at b sub m, then b sub m minus 1, then b sub m minus 2, blah, 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 then b1, then b0, then r, followed by r, it says, we're going to see, for example, positive or 0, negative or 0, positive or 0, negative or 0, positive or 0, negative or 0, positive or 0. So every other one is going to be positive, and every other one is going to be negative or 0. So I had to state this or 0 thing twice. So that's the meaning about the coefficients of q followed by r. And we want to do the same type thing. We want to show that m is a lower bound. That is, we want to take an x value that's even less than m and show the function is not 0 at that x value. It's the same thing we did on the previous slide, except we took x greater than capital M, and we showed f of x was not 0 by showing f of x was positive. Here, we're going to be showing that f of x is not 0, but we're going to have to break it into cases. I'm not going to be able to convert all this alternating between positive or 0 and negative or 0 stuff. I can't convert that into telling you the function is always positive or that the function is always negative. But I can tell you, in these 4 cases, either the function is positive, in which case it's not 0, or the function is negative, in which case it's not 0, at such an x value. So just like in the previous one, it's going to be positive times positive, negative times negative, and adding things together. But we got to break it into cases this time around. Okay, so if x is less than little m, then x minus little m is less than 0. We've got x less than m less than 0. We started with a hypothesis that m was negative, so we get this condition here as well. We're saying all this is we're looking at signs of things. We're finding a bunch of stuff that's negative. Okay, first, suppose m is even and b sub m is positive. So that's the first case. We're going to play with even oddness of m and positive negativeness of b sub m. And that's where the 4 cases will come from. M is even, b sub m is positive. M is odd, B sub m is positive, I see in the shadows. And then we'll do even and odd with B sub m, negative and negative. So we'll get a total of 4 cases. Let's spend the bulk of our time on this first one. The other 3 will be similar. They claim Q of x is greater than 0. All right. Why is that? Well, B sub m is positive, m is even. So here we're taking a negative number x, we're plugging it into Q, so we'll have a negative number for x. We'll raise x to the m power, but m is even. That negative sign will be absorbed, and this x to the m, when x is negative and m is even, this will be positive. B sub m is positive. This term will be positive. If I go 2 terms over, remember we had positive or negative along with a 0. If I go 2 terms over, the same argument works. Over here at B sub m minus 2, the coefficient will be non-negative, positive or 0. And the x value raised to the m minus 2 power, that'll be a negative number raised to an even power. That'll be positive. So 2 terms over, we'll also have something that's positive. So I'll look at every other term and we'll be getting positive stuff out. Well, non-negative stuff out. At B sub 0, this will be non-negative as well. Had we started at m even, skip 2 over, we'll be dealing with non-negative things. Skip 2 over, we'll be dealing with non-negative things. Blah, blah, blah. Skip 2 over, we'll land on B sub 0 at 1 point, and it's non-negative. That's the either positive or 0 stuff. So every other term is either positive or 0. This leading term is definitely positive. B sub m was taken to be non-zero. It represents the degree of the Q function. How about these with the odd exponents? Okay, now you're taking a negative x value, x is less than m, and in turn, less than 0. So x is negative. We're taking these negative x values and raising them to odd powers. Well, that's going to spit the negative sign out. You take a negative number to an odd power, that's going to produce something negative. But remember how the signs alternate? And we started with a hypothesis that this one is positive. Well, if this is positive, then this is negative for 0. If it's 0, this simply disappears. If it's negative, the coefficient is negative. We just argued that the power of x is also negative. We got a negative times a negative, which is positive. So first term is positive. Second term is positive or 0. Go 2 over, same argument works. 2 over, 2 over, 2 over, same argument works. So what we've dealt with here then is this term is positive under all these conditions. This term is, when I say positive, it's non-negative. Next term, non-negative, 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 non-negative. All of these terms are non-negative. That being the case, Q of x is positive. All non-negative, the first one is actually positive. It's more than non-negative. It's not negative and it's not 0. So we get that Q of x is positive in this case, as claimed. B sub 0 is non-negative. That's because of the evenness, and the every other one is non-negative. R must be less than or equal to 0. That's because in this case, we would have coefficients that are positive, negative, positive, negative, positive, negative, positive, negative. We'd have R follow the B sub 0. And when I said positive, most of the time I meant non-negative. And when I said negative, most of the time I meant non-positive, right? Or 0. That's where the or 0 stuff plays a role. And we've got or equals to 0 in these. Then what happens when you take x minus m times Q of x plus R? You know it factors like this. We stated that earlier. This is positive. X minus m hey, x minus m is less than 0. This is negative. Negative times positive, that's going to be negative. To that, we have added something that's negative, or 0, resulting in something that's negative. This is negative or 0. Add them together, you get something that's negative. That is something that's less than 0. All right, there you see the big picture. We took x less than little m, plugged it into the function, and we got out a negative value. That means we didn't get out 0. Then this is not a 0 of this polynomial function. So any x less than m under these conditions is not a 0 of that polynomial function. And it's an argument based on positive times negatives and adding things of the same sign together. Next. Okay. Similarly, except this time, suppose m is odd. A similar argument will show that q of x is negative. Let's look at the first term. So we're taking b sub m positive. Okay, this will be positive. X is still negative. X is less than m is less than 0. So here we're taking a negative x value and we're raising it to m, an odd power. Well, x to the m will be negative if m is odd and x is negative. B sub m is positive in this case. We've got a positive times a negative. That will be negative. And similarly to how we argued in part 1, we can show this one is negative and this one is non-negative, 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 non-negative. Excuse me, I said it wrong, much regrettably. Sorry, this one is negative. And this one is non-positive, non-positive, non-positive. Negative, negative or 0, negative or 0, negative or 0, negative or 0. And then R, we'll flip that one over to non-positive. So we're getting, in the Q function, all these terms are negative or 0. So Q of x must be negative. The first term we need to be strictly negative. And to that, we've added a bunch of either negative or 0 things, resulting in a summation that's negative. So Q of x is negative. Based on the even and oddness stuff, we end up with b sub 0 is negative. Right, do the every other thing, you'll land on this with a negative or 0 sign. We'll follow that by R, and it was going to alternate. So that means R itself will be positive or 0. Right, this is negative or 0, so this is positive or 0 because it follows, followed by R. Now, when we look at this, x minus m, same story. X minus m is still negative. That's negative. Q of x was strictly negative. So we got a negative times a negative. That's positive. And to that, we've added R. And R is positive or 0. Positive plus positive or 0 yields a positive. And so f of x is greater than 0. In this case, in particular, x is not a 0, not a root of the polynomial function f. So again, you choose x less than m under these conditions, can't be a 0. Let's just click through the last 2 cases. As I told you, there'd be 4 cases. We're basing this on the even and oddness of m and the positiveness or negativeness of b sub m. The argument is the same throughout in terms of determining the sign of q of x and the sign of r sub 0. And you know the sign of x minus m throughout this argument, x minus m is negative. So it's a matter of negative times negative plus positive, or negative times positive plus negative, that determines these signs. F of x is less than 0 or greater than 0 or less than, or greater than 0 or less than 0. Anyhow, they're all strict inequalities, and under none of these conditions is the function f 0 for an x less than m. So wherever it is 0 must involve x values greater than or equal to m. In other words, m, lowercase m, is a lower bound for the zeros of this function. All right, so that was a little clunky. Also, satisfying these conditions could be quite messy, it seems. Let's illustrate it with an example. Let's do example 70. All right, find bounds on the real zeros for this function. Okay, this could take a while, and granted, what I've done here is streamline things and made a couple of claims that I haven't justified, but I'm just trying to show you the technique. This is, I don't know how particularly practical this is, especially if we had complicated functions. But we want to find the bounds on this polynomial function. All right. So we need to do a bunch of long division. We need to consider that x minus m stuff. All right. I say, let's try m equals 3. Why m equals 3? Because I probably tried m equals 1 and 2 and it didn't work. Let's try capital M equals 3, looking for an upper bound. We'll take f and divide it by x minus m. Here's the function f, x to the 4th minus 5x squared minus 36. Notice I have to space it out. We're dealing with polynomials here. We've got an x to the 4th term, there is no x cubed term, an x squared term, there is no x term, and then a constant term. So I need to leave those little gaps for when we do the division. We're going to divide this by x minus 3, and we'll find out we get this for the quotient, and we get a remainder of 0. So we've got the quotient function here. Anything catch your eye? All those coefficients are positive. Catches my eye. So all positive coefficients, and this thing down here, actually the remainder is 0. So if we look at f of x written as x minus 3 times a quotient function plus a remainder, we have the quotient function is what we got from the long division with all those positive coefficients, and we had r equals 0. So what matters is the coefficients of q are non-negative and r itself is non-negative. Under those conditions, theorem 4.5.1, bounds on zeros, the first part, the part that was a little less unwieldy, says capital M is an upper bound on the zeros. Coefficients of q are non-negative and the remainder is non-negative. This is an upper bound on the zeros. Can you do better than that? Probably 4 is an upper bound as well. But 3 is a good upper bound because it's smaller than 4. What you do is try 2 and see if you can find a lower upper bound to more isolate where the zeros are. It's not. Well, at least theorem 4.5.1 doesn't tell us that it is. It can't be because we actually saw that 3 is a root because we had a remainder of 0. But this is as good as you can do with 3. Why did I start with 3? Probably I didn't, but I typed it up as if I did, as if it were inside or something. There's a lot of trial and error to find what capital M and lowercase m to use. And similarly, how about we try m equals, lowercase m equals -3, and we'll do the same thing. Where'd the -3 come from? Yeah, probably tried -1 and -2 and they didn't work out. So that's where. Plugging in -3 in x minus m gives us x plus 3. We'll take x plus 3, divide it into the original function. We get a remainder of 0 again. I wouldn't bet on that happening every time. I don't need this to be 0. I just need it to have a certain sign. But look in the q's. It goes, let's see, m is odd in the terminology we had. It's an odd degree polynomial. And it goes positive, negative, positive, negative. I guess I should say positive, negative or 0, positive or 0, negative or 0. And then we got a remainder of 0. So by the notation given in this theorem, f of x equals x plus 3 times q of x plus r, we have q of x is given and r was 0. The coefficients of q are 1, -3, 4, and -12. They go positive, negative or 0, positive or 0, negative or 0, and the remainder, follow it with r, is positive or 0. This is the only one that is 0. So the coefficients in q, followed by remainder r, alternate positive or 0 and negative or 0. So the bounds for zeros theorem tells you lowercase m is a lower bound on the zeros. Can you find a bigger lower bound? Right, I'd want for upper bounds, I'd want to make them smaller, and lower bounds I'd want to make bigger. If I'm trying to find the zeros, I want a little place to look for them. So this time we'd try -2 to see if that's a lower bound. It's not a lower bound, as we could show by trying to use the bounds on zeros theorem. It wouldn't work. In fact, we just saw that -3 is a zero because the remainder is zero. So says the remainder theorem. So that polynomial has zeros between -3 and +3. How many real zeros does it have? At most 4. Can you tell me about positives and negatives? Maybe. I'd look at Descartes' rule of signs, see how many positive and how many negative ones it might have. It changes sign once. Remember, you overlook the zeros in Descartes' rule of signs. Changes sign once. So I would expect it to have one positive zero. But we found it. It was 3. So I haven't found, except by accident, any of the zeros. It just turns out -3 and 3 were zeros, as we saw when we went through the computations from the remainder theorem. But we haven't set out to find zeros. We've set out to find bounds on the real zeros. If you were going to numerically look for them, and there's plenty of software that does that, that software would look here, right? There's no need looking outside here. I know there's at most 4. Could be 3 and -3 are the only real zeros. Could be the other 2 zeros are actually complex zeros. That we didn't look into. All right. We didn't actually find the zeros. This can be hard, can be impossible in a certain sense, in an algebraic sense. So there's a body of math devoted to locating the regions which contain zeros of polynomials. That's what we were just doing with that, that lowercase m and capital M. I know all the real zeros are in here. One classic example is due to Augustine Cauchy. So this would date from about 200 years ago. This would be early 1800s. It states that the zeros of a polynomial function f of x, as given here, a sub n is not 0, really is an n-degree polynomial, lie in the interval lowercase m to capital M, where lowercase m is -1 minus the maximum of the absolute value of a bunch of ratios. Upper bound capital M is capital 1 plus the maximum of the absolute values of a bunch of ratios. Now, this is clean and slick because it doesn't involve any of that stuff with q of x having its coefficients all be positive and the remainder be non-negative and that kind of stuff. Doesn't involve any of that. It says take this polynomial, compute these things, that will give you a lower bound and an upper bound. And all this is taking the absolute value of a bunch of quotients. So that's not hard. This, much more efficient. Proving this is beyond the scope of this course. There are, to this day, areas of research related to addressing these questions. It just so happens I do stuff like this in some of my research, but it's set in the realm of complex analysis. I have a link to a paper here on what are called Enstrom-Kakea theorem results. Click on the link in the notes and it'll take you to that and have a good time. This is a little dated from several years ago, but it shows you that, yeah, this finding zeros thing, this is pretty involved stuff. It's still an area of activity in mathematical research until today and tomorrow and beyond, no doubt. But just a little side comment on that, and a cute result. This result of Cauchy's is way easier than all that stuff that we did. We commented in section 4.1, polynomial functions and models, that polynomial functions are continuous. we didn't cleanly define continuity. You have a good intuitive feel of what it means for a function to be continuous, but we didn't formally define it. We can. It requires calculus, and it requires an idea of limits to define continuity. You'll do it in Calculus 1, about halfway through Calculus 1. The next result applies to continuous functions in general. It's stated for polynomials here in this pre-calculus setting, but you'll see this idea again in Calculus 1, section 2.5, so about halfway through the second chapter that you cover. You'll see it before the midpoint of Calculus 1. The intermediate value theorem says, let f denote a polynomial function if a is less than b, and if f of a and f of b are of opposite signs, then there's at least one real zero of f between a and b. In other words, continuous function, if it's positive here and negative here, it's got to be zero somewhere in between if it's continuous. If it's negative here and positive there, it's got to be zero somewhere in between. So how informal and intuitive is that? Proving it is rather involved, but that makes perfect sense. It can't go from positive to negative without passing through zero. Let's look at number 80, which says use the intermediate value theorem to show this function has a zero in the interval -1 to 0. Polynomial function, we're going to show that this function is positive at one endpoint and negative at the other. That being the case, somewhere in between, the function must be zero. They didn't ask us where, and they didn't ask us to find where this function is zero. They asked us to show that it's zero somewhere in here, not find the zero. Can you find the zero? Can you set this equal to 0 and solve the resulting equation? I can't. I don't think. I could try some rational roots tricks. That's on my mind since we just talked about that. But actually having the algebraic techniques to go through and solve an equation of the form, this function set equal to 0, might not be doable. But that's not what we're asked to do. So good thing. Let's answer the question asked by plugging in -1. Plug -1 into the function, parentheses around the -1 as it's been inserted in these three positions where there's x's, produces a value of -6. The important thing about -6 is it's negative, less than 0. If we plug the other endpoint in, 0, then we get out 2, which the important thing about 2 in this case is that it's positive. So this function is negative at -1 and it's positive at 0. Well, the intermediate value theorem tells you somewhere in between a and b, somewhere between -1 and 0, this function has a 0. With a equals -1 and b equals 0, the function must have a 0 somewhere between -1 and 0. It must have passed from negative to positive somewhere in this interval. Actually, I could even say the open interval because I know it ain't the endpoints because we know what it does at the endpoints. So that's actually fairly useful were you to do a numerical technique. One of the things you might be interested in is, does this actually have any zeros? Because if it doesn't have any real zeros, you feed it to software, you're wasting your time. You're wasting the software's time. Because if it doesn't have real zeros and you're looking for real zeros, you ain't going to find them because they ain't there. So step one in any of the numerical stuff is making sure what you're looking for actually exists. And there's an example in the book where they use the intermediate value theorem to do some numerical manipulations to approximate the zeros of a polynomial function. I believe they do something called the bisection method. So I want to stop the video for this section at this stage. There's a little extra supplemental stuff I want to add, but we'll come back and do that in a separate video related to some things involving cubic functions, third-degree polynomials. And after that, we'll be done with this section. Then we'll look at section 2.6, where we consider finally the fundamental theorem of algebra. That's also considered supplemental and possibly not a topic normally covered in the pre-calculus class, but it's good stuff. And I'll get you a video for it. So have a nice day. I will see you in section 2.5, the second edition, here shortly. Have a nice day.